Hi friends, in this video, let's see question on induction machine. Let's see here, a three-phase squirrel cage induction motor started by D while switching at rated voltage. If the starting current is drawn 6 times of the full load current, starting current is 6 times of the full load current, and the full load slip is 4%, then ratio of the starting developed torque to the full load torque. What they asked? Starting torque to the full load torque is equals to, they are asking this question. So here, see what they given, the starting current is 6 times of the full load current is the one, and the full load slip is 4%, next one. And here the formula, starting torque to the full load torque formula is slipped full load into starting current to the full load current whole square. This formula we derived in the concepts, in starting methods, in starters. So now do it answer. Slipped full load is 4%, and starting current is the 6 times of the full load current upon full load current. Full load current gets cancelled. So 4 by 100 of 36. Nothing but 4 2s are 2 50s are 2 1s are 2 25s are 25 1s are 25. Remaining how much? 25 completed, nothing but 25, 11. 11 nothing but 110, 4, 4 and so on. The starting torque to the full load torque ratio is 1.44. So option B is the correct answer. Here you have to remember this formula we derived already in the concepts. So starting torque to the full load torque is equals to full load slip into starting current to the full load current whole square. And here they given the starting current and full load slip in the given data. This is very simple question but expected question, right? A single phase induction motor driving a fan load. The reason for having, what is the reason for having high resistance rotor to achieve? What is the reason why we are using high resistance rotor? You know that always in induction motor, torque is directly proportional to rotor resistance. If we are using high rotor resistance, then the starting torque also increases, which leads to quick acceleration. This is the reason we are using high resistance in the induction machines. So what is the reason here? Low starting torque wrong, high efficiency wrong, and reduced size wrong, because when extra resistance added, size increases. When extra resistance added, efficiency decreases somewhat because of losses, and due to this high torque will produce not low torque. So the answer is quick acceleration is the correct answer. Let's see, the speed of a 4-pole induction motor is controlled by varying the supply frequency while maintaining the ratio of supply voltage to the supply frequency. That is V by F ratio constant at rated frequency of 50 Hz and rated voltage of 400 volts. If the speed is 1440 RPM. We are using a 4-pole induction motor, speed control is there. Here V by F ratio maintaining constant by changing the frequency, and at 50 Hz 400 volts its speed is 1440 RPM. Then find the speed at 30 Hz if the load torque is constant. Here always load torque is constant, this is must understood. load torque is constant, okay, and they given V by F ratio constant, right? When V by F ratio is constant, when we are changing either voltage or frequency, I said you NS1 minus NR1 is exactly equals to NS2 minus NR2. This is fixed. When V by F ratio constant, when we are changing either voltage or frequency, the change in speeds is equal, same. What is NS1? At 50 Hz 4 pole, 120 F by P minus what is NR1? NR1 is the 1440 is equals to what is NS2? 120 F by P minus NR2. We don't know NR2. So this answer is what is the answer? 1500 minus 1440 is equals to 1500 minus 1440 is equals to 900 minus NR2. If you calculate this, NR2 is equals to 900 minus 60, nothing but 840 RPM. 840 RPM is our answer. 840 RPM is our answer because the change in speeds is same. The change from synchronous speed to the rotor speed, or simply slip speeds are constant. Slip speeds are constant. Slip speeds are constant when V by F ratio constant. When V by F ratio constant, slip speeds constant, then you can get the answer directly. Actually, we have a big process to do this problem, but we have a trick. Simply, the slip speeds are constant. We can get the answer within seconds. Is it okay? Understood? A three-phase, four-pole, how many number of poles? 4. So, three-phase, four-pole, 50 Hz. For 50 Hz 4 pole, what is the synchronous speed? The synchronous speed is 1500 RPM. And they given star connected 400 volts. Nothing but line voltage is 400 volts. What is the phase voltage? Phase voltage is 400 by root 3 volts. Phase voltage. Induction motor has the following circuit parameters. Actually, this is R2 dash. It should be. So what are the parameters? R1 is equals to 1 ohm, R2 dash is equals to 0.5 ohms, X1 is equals to 1.2 ohm, X2 dash is equals to 1.2 ohms. And XM, actually no need of XM for our question. So whatever they given XM. Use equivalent circuit. Use the equivalent circuit. The starting torque when the motor is started direct online is, they want the starting torque. What is the formula for torque? Torque T is equals to P upon omega. What is P? P is equals to 3 I2 dash square R2 dash by S. This is the rotor input I given you in our concepts. So, the torque T is equals to 3 I2 dash square R2 dash by omega. But they want starting torque. To get the starting torque, we have to substitute S is equals to 1 because at starting slip value is 1. So, this is generally the starting torque formula. We have to find out this I2 dash. We know R2 dash. We have to find out I2 dash. How we can get the I2 dash from the equivalent circuit? See, for example, this is my equivalent circuit. And here they given only XM. So here 400 volts supply given. XM is the 35 ohms. What is the R1? R1 is the 1 ohm. What is the R2 dash? R2 dash here R1, R2 dash, this is XM, this is X1, this is X2 dash, and this is RL dash. Here the current flowing is I2 dash. RL dash is equals to formula R2 dash multiplied with 1 by S minus 1. This is generally the equivalent circuit. Can you tell me what is the total reactance? The total reactance is X1 plus X2 dash. What is total resistance? The total resistance is R1 plus R2 dash plus R2 dash plus R2 dash by S minus R2 dash. R2 dash gets cancelled. So the R01 is equal to R1 plus R2 by S. Now what is the current? Here the current is equals to, here the voltage, this is same for here because in parallel. So current is equals to V by Z. So now tell me what is I2 dash? What is I2 dash? I2 dash is equals to V by Z. What is Z here? Z is equals to R1 plus R01 square plus X01 square. Nothing but R1 plus R2 dash by S whole square plus X1 plus X2 dash whole square. If you solve this, you can get current I2 dash. If you solve this, you can get current I2 dash. Okay. So substitute here. V is the 400 upon root 3 and square root of R1. R1 is the 1. R2 dash is the 0.5. S is the 1. So whole square plus X1 plus X2 dash. Nothing but 1.2 plus 1.2. Nothing but 2.4 whole square. If you solve this, you can get the current I2 dash is equals to 81.6 amperes. 81.6 amperes is the current I2 dash. Now substitute here that I2 dash. Substitute here that I2 dash and get the answer is equals to 3 by omega. Omega is equals to 2 pi n by 60. Omega is equals to 2 pi ns. Ns nothing but synchronous speed by 60. 2 pi n by 60. I2 dash square. I2 dash square nothing but 81.6 whole square by S is the 1 and R2 dash is the 0.5. You have to solve this. You have to solve this like this. This 6 goes upside, or you have to get a equation, or you have to solve it. So after solving all these equations, all these numericals, you get an answer of 63.6 Newton meters. 63.6 Newton meters is our answer. 63.6 Newton meters will come. So what we done? Just we know torque is equals to P by omega, where P is the rotor input by omega. For that rotor input, we should know the current. For that current, I draw the equivalent circuit. In that equivalent circuit, current is equal to V by Z. Z is this parameters completely, and I calculated current and I substituted this current and resistance here. So this is generally the starting torque formula. The starting torque is here 63.6 Newton meters. 63.6 Newton meters. This is a very important question. Are you okay? Right? Understood? A three-phase 10 kilowatts 400 volts 4-pole 50 Hz star connected induction motor draws 20 amperes. This is important. Draws 20 amperes on full load. Its no load and black rotor test data given below. No load test and black rotor test data given below. That is rated voltage and no load current and W0, the no load losses, short circuit voltage, short circuit current and short circuit losses they given. Neglecting copper losses in no load test and core losses in black rotor test. Neglected the copper losses in no load test and core losses in block rotor test. Estimate motor's full load efficiency. Estimate the motor's full load efficiency. Let's see. Generally, efficiency is equals to output upon output plus losses. Output is there 10 kilowatts, but losses. In that also, the no load losses are 100 watts. This is fixed. We want copper losses at full load. We want copper losses at full load because we need full load efficiency. But they given the black rotor test results are 762 watts. This is WSC at ISC. Here WSC is equals to 762 watts when ISC is equals to 15 amperes. But we want the copper losses at full load nothing but the current of 20 amperes. The current of 20 amperes. What is the formula? I given you this formula in transformer as well as in induction machine. What is the formula? Copper losses to the short circuit losses is equals to full load current to the short circuit current whole square. This is the formula to find out copper losses at any load condition. If you want full load copper losses, full load current. If you want off load copper losses, off load current. If you want 10% of load copper losses, 10% of load current. So now tell me the copper losses upon short circuit losses is equals to full load current upon short circuit current whole square. If you calculate this, then you can get the copper losses of 1353.67 watts. If you calculate this, you can get an answer copper losses of 1353.67 watts. This is the copper losses I got 1353.67 watts. Now applied here the values. Efficiency is equals to 10 kilowatts upon 10 kilowatts plus 1002 plus 1353.67. Calculate this. You can get an answer. Of 81%. You can get an answer of 81%. The efficiency of induction motor is 81%. So here the thing is that to find the full load copper losses from given data. The formula is this. Copper losses to the short circuit loss equals to full load current to the short circuit current whole square. Then you can get the answer direct. Is it okay? Understood or not? This is very important and expected question. Right? Here, a three-phase squirrel cage induction motor has starting torque of 150%. Starting torque is 150% of full load torque. And maximum torque of 300% of full load torque. 300% with respect to rated torque. At rated voltage and rated frequency. Neglecting the stator resistance and rotor losses. Stator resistance and rotational losses. Then the value of slip for maximum torque. This is you have to find out. So let's see what is the here. The starting torque to the maximum torque is equals to. Tell me what is the formula? Starting torque to the maximum torque is equals to 2 into SMT by 1 plus SMT square. This is the formula. Substitute all the values. Starting torque is 1.5 times and maximum torque is 3 times is equals to 2 into SMT by 1 plus SMT square once, twice. So cross multiply 1 plus SMT square is equals to 4 SMT and bring this side SMT square minus 4 SMT plus 1 is equals to 0. SMT square minus 4 SMT plus 1 is equals to 0. If you solve this quadratic equation, you will get SMT is equals to 0.2679. You will get SMT is equals to 0.2679. Then what is the answer? Option D is the correct answer. 26.79% is our answer. Very simple. Just remember this formula, that is important. We derived this formula. Starting torque to the maximum torque. Starting torque to the maximum torque is equals to 2 SMT by 1 plus SMT square. And starting torque and maximum torque, substitute the values and solve this equation, get the answer directly. Are you okay? Understood? A three-phase squirrel cage induction motor has starting current of 7 times of the full load current. 7 times of the full load current. And full load slip is 5%. Full load slip is 5%. Then the first question, if an auto transformer is used for reduced voltage starting to provide 1.5 per unit starting torque, 1.5 per unit starting torque, the auto transformer ratio should be, here the auto transformer ratio they want, from the common data just we observed starting current is 7 times of the full load current and the slip is 5%. This is the common data for these three questions. So what is the formula here? The starting torque to the full load torque is equals to X square slip at full load and starting current to the full load current whole square. This is the formula well known, you people. Here we want X square. Substitute all the values. The starting torque is 1.5 times of full load and full load. X we don't know and slip of 5% and starting current 7 times of the full load current and full load current. So solve them. These two gets cancelled out. These two gets cancelled out. From this, X square is equals to 100 into 1.5, 100 into 1.5, 150, 5 into 7 square, 5 into 7 square, 49, 245. This is X square. If you want X is equal to square root of 150 by 245. If you solve this, you can get an answer 0.7825. 0.7825. X is equals to 0.7825. Nothing but the transformer ratio is 78.25. 78.25 is our answer for this first question. Just we have a formula. That's it. You can get the answer directly. Now see here. If a star delta starter is used to start the induction motor, the per unit starting torque will be, they want the starting torque, per unit starting torque. And what they asked here, star delta starter is used. So tell me, what is the formula again? Starting torque to the full load torque is equals to, what is for star delta starter? 1 by 3 times of X is equals to 1 by 3. For this, X is equals to 1 by 3. X square, right? 1 by root 3 whole square. Here actually X is equals to 1 by root 3. 1 by root 3 whole square is the 1 by 3. So 1 by 3 into slip at full load into I starting to the I full load whole square. Now I want starting torque, that is equals to 1 by 3 slip at full load 5 by 100, 5%, and this is 7 times of the current by current whole square. These two gets cancelled out. So this is starting torque to the full load torque. Now tell me, what is the answer? The starting torque is equals to, this is 49 into 5, 245 by 300. 245 by 300 of full load torque. So can you calculate this? 5 fours are 20, 5 fours are 20, 5 nines are 49, and 5 six are 60. Around 50 by 60. Around 50 by 60. 5 by 6 nothing but how much, sir? Can you tell me what is 5 by 6? 5 by 6 nothing but 0.50. 6 eights are 48. 6 eights are 48. 2 is there. Nothing but 20. Around 3 is up. Nothing but our answer should be 0.8 something. So what is the correct answer? Here, if you calculate this, you can get an answer 0.816 per unit. 0.816 per unit. So option B is correct answer. Just here x is equals to 1 by root 3. 1 by root 3 whole square is equals to 1 by 3. 1 by root 3 whole square is equals to 1 by 3. Then you can get the answer directly. 0.816 per unit is the starting torque per unit. This is the second question. Are you okay? This is the second question. Next, third question. Let's see here. If your starting torque of 0.5 per unit is required, then per unit starting current. Now they want per unit starting current. So see here again, starting torque to the full load torque is equals to simply slip at full load, and starting current to the full load current whole square. Right. What is starting torque they given? The starting torque is 0.5 per unit of full load torque, and full load torque is equals to slip 5%, and starting current we don't know, and this full load current we don't know, whole square. Now these two gets cancelled out. So this comes here. What is the answer? 50 is equals to. So what is the answer here? See, 50 by 5 is equals to starting current to the full load current, here square root. Yes or no? 100 into 0.5, 50, and 5 comes here. Starting current to the full load current whole square, but square comes here square root. 5 ones, 5 tens. So now tell me what is final answer? The starting current is equals to root 10 times of the full load current. Root 10 nothing but 3 3s are 9. So what is the answer? 3.16 per unit. Yes. A 230 volts, 50 H, 4 pole, single phase induction motor is rotating in clockwise direction at a speed of 1425 RPM. If the rotor resistance at standstill is 7.8 ohms, then effective rotor resistance in the backward branch of the equivalent circuit will be. First see the equivalent circuit of the single phase induction motor. See, this is the forward branch, and this is the backward branch. Here xm by 2, here r2 dash by 2, here xm by 2, and here r2 dash by 2, and here xm by 2. But here generally torque is equals to I2 dash square into R2 dash by S into omega. If it is 3 phase, 3 into I2 dash square into R2 dash by S. But for single phase, forward torque and backward torque resistances are, for forward torque the resistance is R2 dash I2 dash square into R2 dash by 2s of omega, R2 dash by R2 dash by 2 s omega. This is the forward torque effective resistance. Forward torque effective resistance. What is the backward torque effective resistance? Here, backward torque is equals to I2 dash square into R2 dash by 2, R2 dash by 2, but this is backward. For backward, what is the slip? For backward, the slip is 2 minus s. For backward, slip is 2 minus s of omega. The effective rotor resistance in the backward branch of equivalent circuit is R2 dash by 2 into 2 minus s. R2 dash by 2 into 2 minus s. Hence, the RB dash is equals to simply R2 by 2 into 2 minus s is enough because they given only R2. So, is equals to, what is R2? 7.8 upon 2 into 2 minus s. Oh, what is the s? This is a 4-pole 50Hz machine. For 4-pole 50Hz machine, ns is the 1500. But here nr is the 1425. So the slip is the 75 of 1500. ns minus nr by ns. 15 5s are 15 1s are. So what is the slip here? What is the slip here? Here slip is the 5%. Slip is the 5%. So here the slip is the 5%. So calculate this. Calculate this fast. 7.8. 7.8 2s are 3.9 of 200 minus 5. 195 into 100. 195 into 100. So finally the answer is 390 of 195. 195. So tell me what is the answer? Tell me what is the answer? 200 minus 5, 195, and 2 and 100, 3.9. So what is the answer? This is 195, 390 by 195. So answer is 2. What is the answer, sir? 2. Yes or no? 200 and 180 and 10. That is the answer is 2. Answer is 2 ohms. Simply the answer is 2 ohms. This is our answer. R2 by 2 into 2 minus s. Here the effective standstill resistance they given. R2 they given. So R2 by 2 into 2 minus s. R2 by 2 is the 3.9 and 2 minus s is the 2 minus s. S is equals to 5%. 2 minus of 5%. 200 minus 5, 195 by 100. So we can get the answer is 2 ohms only. So this is the question on single phase induction motor. Very important. Right? Understood? Thank you.